Welcome back to Chemical Study Zone. I am DVK Bhagwan. In the previous lecture, we discussed about the Reynolds transport theorem and the integral mass balance for the incompressible fluids. And now in this today's lecture, I'll discuss about the integral mass balance for the compressible fluids and its uniform flow for compressible fluids and the average velocity. And in the next classes, I'll just discuss the integral momentum balance, integral energy balance. Okay, so for to get the notifications, please subscribe to my channel. Now let's start the class. Okay, integral mass balance for steady state, for steady flow. That means for steady flow means the fluid may be compressible. As for steady flow, Cv is constant throughout the flow. That means derivative of Cv equals to 0. Okay, here we have the equation which we have proved yesterday for the integral mass balance as dou by dou t of integral of Cv rho into dV plus integral of Cs rho of V bar dot dA bar equals to 0. As we said that the derivative of Cv is 0 for steady flow, that means this term again will be 0. So we left with only this term, integral of Cs rho of V bar dot dA bar equals to 0. This value equals to V bar dot A bar equals to V into A for outlets and equals to minus V into A for inlets. So for uniform properties, we consider uniform properties. What they actually mean? That means rho, density and velocity are constant at each control surface area. That means the integration of this term will give us the sigma of all the control surfaces present in the system of the V bar dot A bar equals to 0. That means we can split this equation as sigma of control surface outlet of rho I Vi Ai bar minus the sigma control surface of all inlets of rho I into Vi bar dot Ai bar equals to 0. That means sum of the all outlets minus sum of the all inlets gives us the value 0 for the uniform properties. That means we can simply write it as sigma of all inlets rho I into Vi bar dot Ai bar equals to sigma of all outlets rho I of Vi bar dot Ai bar. This is the equation we got, this very main. And if we consider only one inlet and one outlet, then this equation will be rho inlet into Vn bar dot A in bar equals to rho out of V out bar dot A out bar. This is the equation for one single inlet and for single outlet. Now let us prove this equation for the uniform flow. for the uniform flow, how the integral mass balance will look like. Okay, before this proving, let us we should have to draw a figure for just proving these terms. Sorry. Yeah, let us consider a pipe which is very rigid. That means it is stationary in its motion, and let us consider a fluid is flowing into it. Let the height of this pipe be 2b. Okay, actually we know for the uniform flow the flow will be in this direction. That means the laminar flow. In the laminar flow we have the V max at the center, and the velocity that means the velocity is maximum at the center, and the velocity at the walls is 0, and the velocity gradually decreases as we move from center towards the walls. Okay, and consider the width of the pipe be W. Okay, that means at center V is maximum, and at walls V is minimum. Sorry, V is 0. Okay, now as we can see, that is a parabolic graph. Parabolic, I can write it as simply the V of y, the velocity profile of the gas is V max into 1 minus y by b whole square. As we know that as we should have to find the volumetric flow rate. Volumetric flow rate in this condition is nothing but q dot equals to integral of v bar dot dA bar. So I'll substitute this v value in this equation, then we will get integral of v bar dot dA bar equals to integral of v bar this v of y into the area, which is nothing but this length. I'll consider this length for a small system. I'll just calculate it. That means it is dy into w into y bar. As we are considering only it's in along x direction. That means after multiplying this equation with here, we will get equals to plus b vx into dy, and after now let's substitute this value of vx, which is nothing but the vx of y here. Then we will get the volumetric flow rate as v bar dot dA bar equals to w into minus b2 plus b v max into 1 minus y by b whole square. This is the volumetric flow rate for the uniform flow. And average velocity, as average velocity is the V average equals to the volumetric flow rate by the area. So gives us the volumetric flow rate. The area is nothing but 2b into w. Now as we know, if flow is uniform, the Vx is independent of y. That means the velocity vector in along x direction does not depend on the direction of y. That means integral of v bar dot dA bar equals to integral of vi bar into dy into w of I bar. That means we will get only w of minus b2 plus b u into dy, which is nothing but the q dot the volumetric flow rate equals to u into 2b into w, where u is the velocity in x direction. So let's substitute this q value over in this equation, which is q dot by 2b in w for getting the average velocity. Then we will get v bar average equals to q dot by area, which is equals to u into 2b into w by 2b into w. These two terms will get cancelled and we left with only the v average velocity equals to this u. So the average velocity is nothing but the velocity which is moving in the x direction. So this is for today, as we have proved the integral mass balances for the incompressible fluids and the uniform incompressible fluid, and now we have proved for the steady state and for the uniform flow. And in the next lecture we will discuss about the integral momentum balance, which is a big equation to derive, but it will be simple in solving. Then we'll just go to the limitations of the the applications of the integral momentum balance for the laminar and turbulent flow, and next we go into the integral energy balance. Then we will go for the differential balances of the against for the same mass, momentum and energy. Okay guys, if you like this video, please like, share and subscribe to my channel, and don't forget to hit the bell icon to get the many more updates.